Alrighty. Hi there. My name is Alex Smith. I'm a senior here at Brigham Young University studying mechanical engineering. I'm in this class, Deep Learning for Engineering, or for engineers, ME 595R. This is my final project, the BYU Racing Team's chassis evaluation. So, as a summary, the goal of this project is to predict the stiffness of a race car tube frame chassis using attention-based neural networks. Okay, so the motivation for this project comes from the design process of building the tube frame chassis. This car is built as a one-off car every year by BYU Racing Team, the club here on campus. And so needing to iterate quickly is of high importance. We have the academic school year to build this car, and we need to be able to converge on a design that will both be stiff for handling and safe and low stress for the drivers. And so like you can see there, the overarching goal is to be able to predict the stiffness and stress from the geometry characteristics of the frame and the loading conditions. So where do the data sources come from? This is from our 22 ANSYS simulations, being able to give us stress and deformation information. And so of those 22 ANSYS simulations, we really use 11 core trials, of the ANSYS, and that is also combined with the 6 physical trials where we have the stress developed from the strain gauges as well as the deformation information for each of those trials. So we are able to take the inputs also of tube geometry from each of these different iterations, the boundary conditions as well, and being able to know whether one end of the car is fixed or simply supported and the other one is twisted. In the torsion test that we perform, which this is mimicking, is we have one end of the car that is fixed to a surface that is unmoving, and then the other side of the car is twisted at the suspension points to be able to get torsional stiffness. So 11 trials is not a lot of data, especially not for a neural network. And so to be able to get more accurate predictions, I needed to augment the data. And you can see here the details on how that was done, what kind of augmentation was performed. So we were able to boost the data set from 11 trials to 75. And so this was able to help us predict better, versus what you can see here on the right. The predictions are very far off from that line. They're all in line, or the predictions in general are not very good. And that's not very helpful for us. And so we're able to improve the generalization and reduce overfitting by augmenting the data. Ideally, in the future, this does not have to be done because there will be more data as the years go on, and the teams will accrue more information from each year as they go and design new cars. So, talking about the neural network architecture, as an overview, neural networks generally take a set or fixed size of inputs. And the main difference with this project is that chassis designs vary from iteration and having a different number of tubes, a different number of tubes with different sizes in their wall thicknesses or outer diameters. And so these different features are variable. And so this code that I've built, this neural network, is able to unpack these Excel folders or files with all of the chassis information, with their setup and their loading conditions, as well as their intrinsic features themselves. And so they're able to take those features and put it into this encoder that we're able to use to treat each tube separately, and be able to use this net encoder to turn each tube into a learned vector. This is a concept borrowed from GNNs. Then we use attention to learn which tubes matter the most. So a tube that is thicker or longer and is bent might be more important than a tube that is shorter or thinner and may not be bent. So multiplying these two vectors by attention weights gives us our weighted average, which tells the network whether or not it's important, how important it is. Then we're able to compile this all into a single level chassis vector, which is better for a neural network to learn is a fixed size summary. We pass this into our second neural network, which is physics enforced to be able to predict torsional stiffness and stress. We added dropout in this neural network so that it can learn better, generalize better. And so a little bit more here in the nitty gritty. There are six classes we have. So the aggregator, which takes all of the tube information and compiles it into one. And then these next four, the stiffness, stress, deflection, and torque predictors are also part of this. And all of these get combined into this physics-informed chassis network, which is the main neural network. It compresses all of these to a single vector for predicting the torsional stiffness and stress and use the physics to enforce learning, especially for the stiffness. So all of these aggregators or predictors are um, three layer MLPs, and they have a layer width of 32 and 16 for the aggregator, and then layer widths of 64, 32, and 16. All of them using SILU as the activation function, and so they're able to predict all of the stress. And the not only does the network predict it directly from the data, but it also is able to do this using the physics informing for it. So it also learns it indirectly, using penalties if the physics don't match up. So as we go into the training and loss, you can see here, this is one of the training versus testing plots that we have from learning about this project and getting to a point where now we're in this final deliverable. Using 1500 to 2000 epochs really gives a good sense of whether or not this is learning properly. In between that has been kind of ideal. Using more than that is too much. It's overkill for this project since there really isn't that much data to be training on in the first place. Using less doesn't capture the scope very well. I enabled GPU for this project because my computer, the CPU doesn't handle it super well, so GPU is better for it. I have a better GPU on my computer. And then MSE loss is extended with our physics-informed loss as well. And then we've trained and validated this on a 70-30 split with our data. So using the optimizer atom and reducing our learning rate, we got these results here. We have the torsional stiffness and the stress analysis here, also predictions. And you can see here the scatter plot actually lines up fairly well for the stiffness predictions. Because the data is augmented, there are these higher values. We would be expecting something around 2000 Newton meters per degree or lower than that. And so all of these higher predictions for stiffness are likely due to the data augmentation. And then on the other hand, with stress, this network actually predicts very well that the stress will actually not reach higher than 600 MPa. This is good. Our ideal stress should be under 435 megapascals. Again, because of the data augmentation, it's possible that some of these predictions are higher than 400 or 500. But what we're looking at here is very good as the cluster of the predictions center mainly under 600 or 400 megapascals. So what does this mean for the team? Now we are able to get pretty much instant feedback on our new designs. So a new member could take our information of the car, for example, the number of tubes, the thicknesses, all of that, extract the data from the design, be able to import that into this neural network. And this will allow them to filter out poor designs early, to be able to converge on better designs, hopefully taking much less time than we did this year and be able to converge on a really nice design early on and be able to get into the manufacturing process as soon as possible. This is ideal because the frame of the car holds everything else on it. And so having this early allows other teams to be able to optimize their designs and doing physical testing. So this is a project that is totally scalable. If a team member wanted to take this and predict the mass, that's something that can be built into this structure instead, or in addition to the things it already does in predicting what the optimal where there is diminishing returns when minimizing weight and in trying to increase stiffness. A really awesome application of this would be to add geometry aware GNNs to this so that you can actually see the stress and stiffness happening on the car and be able to have these design conversations happen quicker. So as a conclusion here, this can replace time-consuming FEA iterations early on so that we can converge on designs quicker. Like I said in the previous slide, it's very easily extendable and it's already going to be able to be deployed here in the next coming months as we start the design process over again. And this has been a great project to learn more about applying neural networks to the frame of this car. Thank you.